Hello, this is Yusuf. I am a mechatronics engineer, graduated from the University of Jordan in June 2021. Today I'm going to present a design of the Cyratron control system for series motors project under the supervision of Professor Sarkar, and thanks to him for his supervision. The content of this course, first of all, introduction. I'm gonna present the Cyratron and the Cyratron background and what it how it operates. Second, project specification, the specification of the whole project from its parts and all of this. Third, Cyratron design, the design itself of the Cyratron itself, and finally a conclusion of our design and how to improve it. First of all, the introduction. Cyratron tube is a tube filled with gas and used to control for, let's say, for switching and rectifier. It can be filled with hydrogen or neon or mercury vapor gases, and it depends on Bastian's curve, which is give us the breakdown voltage according or versus the hydrogen gas which is used. The construction of Cyratron is anode and cathode, hot cathode, a control grid, and filament. The filament is used to heat the cathode, heat up the cathode to reach a suitable value. The operation of Cyratron. First of all, before the operation, we can use a supply voltage or supply power, DC or AC supply power. But in this project, we will use AC supply power, then transfer it to a DC supply source to control a DC load. So we have to use a DC supply voltage. The operation of Cyratron is the operation of Cyratron. If the DC if the power supply is the DC, so it will not be on. It will be off. If the power source across the Cyratron is open, the Cyratron will be closed until a voltage pulse from the grid will break down the Cyratron and allow the voltage to pass through the load. So we have two conditions to open the load. First one is the voltage source across the Cyratron, and the Cyratron must handle this power source. The second condition is to give a pulse to the grid to open the Cyratron and to transfer the voltage to the load, a DC load. To turn off the load, we have also two methods. Let's say the first one is to shut down the voltage source, DC voltage source, where the anode voltage where the anode will be near to zero or zero, and this will turn off the Cyratron, and the load will turn off also. The second one is to also give a negative voltage, negative pulse to the grid to turn off the Cyratron again. And and the Cyratone will be ready for the next pulse or next cycle. What is the difference between Cyratone and thyristors? First of all, thyristors are current control semiconductor devices. They consisted of 4 layers of semiconductor material. 2 of them are N-type and the other are P-type, forming together in 3 junctions, producing 3 terminals, such as the thyrotron, anode, cathode, and a gate terminal. The gate terminal in the thyristor is the same as the grid control in the thyratrons. Also, in thyristors, there is no need for filaments. Thyristors are more reliable and more efficient than thyratron due to internal losses and less lifespan because of the heating of filaments. Thyristors are non-semiconductor material and they are voltage control devices. Both thyratron and thyristors can be used as switching devices and rectification process for rectification process. Project specifications. This is the part of the parts of the project. The first part is AC power supply, which will be like in Jordan, 230 voltage source, and 50 hertz as a frequency. The second one is step up transformer. We need to step up the voltage to 100,000 voltage, and that's and this value is the load of the rated voltage, rated DC voltage, and the voltage that can handle, and the voltage that we designed the thyratron based on it. So the third the third part, uncontrolled rectifier. So we will transform the AC power source to a DC power source because of the load, which is DC motor. So we need a DC load. Then we have 2 optional parts, which is the filter circuit and regulator circuit. The filter is to filter the signal from the uncontrolled rectifier to be constant and constant as possible, and the regulator circuit to ensure a rated DC value to reach the DC motor. So it will not be like less than the rated or more than the rated, because of the AC power source will be change based on the grid we have. And finally, the Cyratone itself, which is the switching device that will control the DC motor. The third part, Cyratone design of Cyratone itself. Before the Cyratone design itself, we have to know the circuit we will going to put the Cyratone in it. So first one is the Cyratone itself, and there is the control grid. Here the control grid will be controlled by pulses, triggered voltage pulses to control the Cyratone. Here's the load, DC load, and here is the PL or pulse forming line or pulse forming network to ensure a constant DC power to the load. So we will in this PL we will use 250 ohms network. The inductor will be 138 microhenry, and the capacitor will be 0.001816 microfarad, and the L, the inductor here, will be 56 Henry. EC here, or ER, is the voltage pulses supplied to the grid to control the grid, either positive voltage or negative voltage, and it will be like a sinusoidal signal. For the grid trigger voltage, we will use the signal with amplitude from 200 to 500, duration 2 microsecond, phase of time 0.3535 microsecond, and the impedance will be from 50 to 500 ohms. Design principle and operation characteristics. Here the ER, which is the voltage, grid trigger voltage, will, if it's positive cycle, if we perform a positive cycle to the grid, the thyratron will open and the load will turn off. And after that, if we turn off the ER, the voltage trigger, the load will be turned on, as long as the anode voltage is not going, or not close to zero, not be zero. The anode voltage, which is the DC power source. Yeah. But if we perform an AER negative cycle with negative voltage to the control grid, the thyratron will close and the load will turn off. Design and construction of thyratron. As we told earlier in this presentation, the peak forward anode will be 100 kilovolts, peak anode current 350 amps, distribution rate 1000, pulse width 1 microsecond, average anode current half ampere, and P factor, which will be 20 multiplied by 10 to the 9, which is 20 mega. Tube pressure will be half turn, and electrode gap distance will be 1.8 centimeter. We will use a 4 gap, which is 4 electrodes. 4 electrodes design, and the gas will be hydrogen gas, which the hydrogen gas will give short deionization, unlike the other gases. This construction of thyratron will needs 4 voltage pulses for each one of them, and will be a ceramic material. The tube itself will be a ceramic material, ceramic metal thyratron. And here is the Batchen's curve, as earlier told. Here is the voltage, breakdown voltage, and here's the P dot times T, which is the pressure times the electrode gap distance. So half multiplied by 1.8 will be 0.9, which is here 0.9. This blue curve, which is the hydrogen. So we get 100,000 volt breakdown. Thyratron methods: triggering, correlation, conduction, and recovery time. triggering a positive pulse causing electric failure in the high voltage region. So, okay, by forming plasma in the cathode region, and it will conduct the relationship between the plasma generated in the anode region and the plasma region present in the cathodic region. This is the correlation. Then this process will, the conduction method directs a constant voltage. After uh, these two methods, after this happened, the conduction process will take place. These two methods will have will take 120 to 200 nanoseconds take place because of the plasma forming plasma in the anode and the cathode, and to conduct and to the electrons, to move the electrons to the other side, to the cathode. Finally, the recovery time, Cyratone switch open with the release of ions in the inner wall, and electrode servers using negative voltage to the control grid. So the negative voltage to the control grid will switch the Cyratone off, and the load will be off either. And this recovery time will take up to 30 to 150 microseconds, depending on type of pipe itself or tube, the internal pressure, and the type of gases it uses. We use as told earlier, as told earlier, we will use a hydrogen gas because of the short deionization that will make the Thyristors. And this time recovery time required is dependent on the gas in the tube, which is the hydrogen, and as told earlier, the hydrogen is have a short deionization, unlike the other gases. Evaluation of Cyratone. Our Cyratone is not the best and the higher efficiency in the all Cyratone. No, there is a there is much higher efficiencies, but the design will be much harder, because for example, let's say the lifespan of the Cyratone itself had to be taken into consideration. If we have 100 kilovolts, 10 kilowatt, and 1000 BBS, and the PP factor is this numbers as our specifications, because the unexpected short lifespan will happen. This anode plate was found to be strongly eroded, so the anode will be eroded. Erosion will happen at the impact areas of the discharge, and high voltage breakdown. So the ceramic envelope extension at the anode cap became a typical cause of failure. So the lifespan of it will be short, depending on the other material. Anode region was reduced by operating. This is the if we want to perform or higher the efficiency of the Cyratone tube under the sufficiently high gas pressure. This was not a problem as research showed. So we have to add a reservoir. Reservoir ranges were always wide and high, fairly high upper limits to inject the tube with the right amount of gas, and to ensure a high pressure and constant high pressure in the tube. Also, we have to add a titanium hydride in the reservoir itself, containing 2.5 grams of hydride and approximately 30 millimeter of hydrogen. These changes will improve the design and increase the Cyratone lifespan. So this is the improvement. We want to add an improvement to our design. Finally, a conclusion. A peak forward voltage capability above 100 kilovolt is indicated by this investigation. It is expected that the development beyond this voltage level will have to deal with the problem. So 100 kilovolt is not a normal voltage, it's very high voltage. So if we reach that or above it, there will be a problems. Requirements on the dielectric strength of ceramic material and the anode plate material and the design will be very high. So it will be much more expensive and very hard to design above the 100 kilovolt. Our design is basically a good one because of the ceramic material, Cyratone, and not that hard. So it's a simple one and easy to construct, and also the circuit itself is not that complicated. Finally, thank you for all for listening, and thank you for everything. I'm sorry if I done anything. Thank you.